Okay, so today we're going to be doing the first derivative test, talking about it, but dealing specifically with doing it with piecewise functions and absolute value functions, okay? So, first derivative test. So, what we're going to do for this following piecewise function is we're first going to find the critical numbers, then we're going to find the open intervals on which the function is increasing or decreasing, and then we're going to apply that first derivative test to identify all the relative extrema. Okay, now these are basically the same steps that we follow every single time we do a first derivative test. The only difference is that we have a piecewise function. So the only thing that's going to happen is that when we take the derivative of this function, we're actually going to have to take the derivative of both pieces of it. Okay, so we still have our piecewise function. When we take the derivative of 4 minus x squared, we get negative 2x. And that's the slope when x is less than or equal to 0. Then in the second one, the derivative is negative 2. And that's when x is greater than 0. So these are my slopes. So all I did was take the derivative of each piece separately. Okay, so it's just like we've been doing. The only difference is that we might have to take the derivative of multiple pieces of it. Again, we're still, to find critical points, going to set this equal to 0. The difference is that we're going to have to set each piece equal to 0. So the first piece, negative 2x, set it equal to 0. Sorry, my pen's running out of ink. And then the next piece equal to 0. Well, this is not going to have any critical points. And this one, the critical point is at 0. So for part A, our only critical point is when x equals 0. Now, part B is asking for the open intervals where it's increasing or decreasing. And this is basically setting up the number line for the first derivative test. So we set up our number line. We only have one critical point to worry about at 0. And then we're going to pick a point on this side. Well, when I pick negative 1 and I'm doing my first derivative test, I'm plugging it into the derivative. And negative 1, I use negative 2x. So negative 2 times negative 1 is positive. So this side is positive. When I pick 1, that's when x is greater than 0, and my slope is always negative. So if you remember from our earlier notes, it said that when slope is positive, my function is increasing, and when the slope or the derivative is negative, my function is decreasing. So this gives me my answer to part B. My function is increasing when the slope is positive, so that's when x is less than 0. That is when my function is increasing. Or you could write it as negative infinity to 0. Either way. And my function is decreasing when x is greater than 0, or from 0 to positive infinity, however you want to write it. Okay, so that's part B. And then part C says to identify any relative extrema. Okay, well, right here at 0 is my critical point, and my function on this side is increasing, and on the other side it is decreasing. So if my function goes from increasing to decreasing, this is a maximum. So x equals 0 is a local maximum. Okay. Now, being able to graph these, to visualize the graph, would make this a whole lot easier. So if we looked at what this piecewise function would look like, my quadratic is been reflected over the x-axis. That's where the negative comes from, and shifted up 4. So 1, 2, 3, 4. So this piece looks like this. And then the negative 2x basically looks like this. So you can see from the graph very clearly that 0, that's where my maximum is from the graph. All right. Now, very similarly, when we look at absolute value functions, it's very similar because, and this is one of those things that I don't like when people call the absolute value function a parent function, because technically it's not a parent function. It's actually a piecewise defined function. So for an absolute value function to do critical points or extrema, I actually have to split it up into its two pieces. And this is actually, the first piece is going to be x plus 4, which is wherever the equation is. But there's another piece here when it's negative x plus 4. And where does this switch? Well, it switches where the vertex is. So this one is going to be when x is greater than negative 4 or equal to. And this is when x is less than negative 4. Okay, so what I had to do here is I actually had to take my absolute value function and split it up into two pieces. And then basically it's very similar to the problem we did just a minute ago with the absolute value, with the piecewise function. So the first thing we're going to do is find the derivative. So f prime of x equals, so this is positive 1 and this is negative 1. Okay. So again, thinking of this graphically will kind of help us. So if I graphed my piecewise function, the transformations basically, my absolute value function's been shifted over and it looks something like this. Okay? So I know since I'm on a closed interval, I'm going to have to, since I'm looking for absolute extrema, I'm going to have to check my endpoints as well. So I'm going to have to find f at negative 7 and f at 1, and I'm going to have to check any critical points or where the derivative is undefined. Well, the derivative is undefined where it is not smooth or continuous. So for this function, I'm going to have to check this point at negative 4. That is a critical point because my derivative is undefined there. Okay? Or you can see very clearly the slopes here do not match. On one side it's positive 1, on the other side it is negative 1. And if you remember, the derivative is a limit. And where the limit fails to exist, the derivative fails to exist. So here you can see that this 2 points don't match. So it is discontinuous there. Okay, so there's a critical point also at negative 4. So that's what we're going to have to check at negative 4. So we plug all of these values in to our original function. So we plug negative 7 in. Negative 7 plus 4 is negative 3. Absolute value makes it positive 3. When you plug in 1, you get 5. When you plug in negative 4, you get 0. And you can see from these that your absolute maximum is at 1. That is your absolute maximum value. And your absolute minimum, therefore, is at negative 4, which is our minimum value of 0. So the only difference between the problems that we've been doing, finding critical points, and then using the first derivative test, is that here you have to account for those breaks. Okay, those breaks in the domain. And again, if the limit fails to exist there, the derivative fails to exist there. And in the first case, there was a jump discontinuity. and that's what caused that critical point, or that where the derivative failed to exist. And in this one, it's not smooth, so that's where our derivative failed to exist.